So this is our unit about permutations, combinations, and binomial theorem. The first lesson is about permutations, and that's lesson 11.1. So imagine you're packing for a trip. You decide to take 3 different tops and 2 pairs of pants. If all these items can go together, how many different outfits can you make? Well, we want to show that we can do this using 2 different things. So one way that we can do it is using a tree diagram where we list top number 1, top number 2, and top number 3. Well, top number 1 can be paired with the 2 pants. So pant number 1, pant number 2. And then top 2 could be paired with the pair of pants as well. So pair 1 and pair 2. And then the third top can be paired with the first and second pair of pants. So as you can see, how many total branches you have will create an outfit. For example, this is one outfit. And then we have 2 outfits, 3 outfits, 4 outfits, 5 outfits, and 6 outfits. So together there are 6 total outfits that can be made. A fast way of calculating this is by taking the stages that you have to choose. Well, we have tops and we have pants that have to be chosen. So how many tops are there? Well, there's 3 tops and there's 2 pairs of pants. And what we do is we multiply these numbers together to get our answer of 6 outfits. So this is the easiest way to figure this out, or the easiest way and fastest way is using this kind of multiplication. So let's say you also take 2 pairs of shoes. How many different outfits consisting of a top, a pair of pants, and a pair of shoes are possible? So just like in the previous case, instead of 2 spots now we have 3 spots. 1 spot for the top, the second spot represents the pair of pants, and the third spot represents the shoe choices that we have. So we have 2 tops. We have actually 3 tops. We have 2 pairs of pants, and they're telling us that we have a pair of shoes. We have 2 pairs of shoes, so there's 2 choices there, and then we multiply between these numbers, so that's going to give us 12 outfits that can be created. Number 3, determine the number of outfits that you can make when you take out 4 pairs of pants. So pants is a spot, and we have 4 choices, times there's 2 shirts, and there's 2 hats that can be created. So if you multiply all these numbers, you get 16 different outfits. So make a conjecture about how you can use multiplication to arrive at the number of different outfits possible in steps 1 to 3. So all you're taking is, you're taking your pairs, your choices of each pair of clothing, and multiplying. So a friend claims that he can make 1,000 different outfits using only tops, so that's one stage that you have to choose, pants, and shoes. So is he correct? Well, yes, because you could multiply 3 numbers, and as long as they give you 1,000 in total for outfits, then this would work. So one possible arrangement is I could have 10 tops, 10 pairs of pants, and 10 shoes, and that could create 1,000 outfits. So this would be one possibility. Now there's many answers for this. So what we were just doing is we were doing the fundamental counting principle, where we take one task performed A ways, and a second task. Now these tasks are like the clothing, right? So what we're choosing is the top, pants, so that's our second task, perform B ways. And what we're doing is we're multiplying these two ways together. How many choices we have are being multiplied. So example number 1, we have four possible applicants for 2 different positions at a department store. In how many ways can a manager fill the positions? So for A, we know that there's 2 different positions in the department store, and there's 4 possible applicants. Well, that means for the first spot, we have 4 choices. Now, once we place a number there, we have used one of these people. So now for the second position, we now only have 3 applicants left since we have placed someone in the first spot. So when we multiply, there are 12 possible ways that we can fill this position. For B, it says, how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats? So what I like to do for these cases is write out how many spots there are, which are 7. So there's 7 seats, so I write 7 spots to represent that. They want 3 boys in a row, and if a boy must be seated at each end of the row. So there has to be a boy. Well, we have to first look at how many boys there are. We know there's 3 boys, so we start with the boys on the ends. So if there's 3 boys, I'm going to put 3 here. Now, once we place a number in any spot, that means it's going to be 1 less for the next spot. So I have now 2 boys left to place in that on that other end. And now we're placing the other people in any of the remaining spots. Well, we have 4 girls left and 1 boy. Together, that means that there are 5 people left to place. Well, that means I have 5 choices for the second spot. Once I put a number in, there's always 1 less for the next spot. So that means there's 4 people left, then 3, then 2, and then the last person is going to be placed here. Now, what we always do is we multiply between all these numbers to get our final answer. So if you put this into your calculator, you should get 720 different ways that they can be arranged in this row. Example number 2, it says use any method to solve each problem. How many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5? Repetition of digits is not allowed. So for A, we have a 3-digit number, so we're going to represent that with 3 spots. And the reason we're using spot is that it's like a placement. It's like a stage that you're selecting. So I'm selecting the first digit, the second digit, the third digit, which is why there's 3 spots. So they're saying, how many ways can you make a 3-digit number? Well, we have, in this case, 5 choices. So repetition is not allowed. So that means that if I put 5 of the numbers, so if I have 5 choices, there's 5 numbers that could have gone into the first spot. Once you place a number there, there's 1 less for the next spot and 1 less for the third spot from that second spot. So as you can see, there's first 5, then 4, then 3 choices for the 3 spots. When you multiply them, you should get 60. For B, now they're saying that, how would it change if repetition of digits is allowed? Determine how many 3-digit numbers can be formed that include repetition. So now they're saying that we can use all these numbers again and again and again. For example, the first spot, we still have 5 choices because we can use numbers 1 through to 5. Now, because once I place a number down, I can repeat the number that I used in the first spot. Now there's 5 choices again for the second spot if repetition is allowed. And finally, 5 numbers again for your third spot as choices, which gives you 125 options. So when they allow repetition, there's always going to be more options, more ways that can be done. Example number 3 is a final score in a soccer game is 5-4 for Team A. How many different halftime scores are possible? Well, there's 2 spots, right? 1 spot for the first team and 1 spot for the second team. Well, what is available? What's an option that can happen is the final score for a team. So if we know the final score for a team, we have to look at what could have happened. For the first number, that 5 is an option. It could have been 4, it could have been 3, 2, 1, and it could have been 0. They could have had at the halftime no points. So there's actually 6 options for that first number right here. And then for the 4, how many choices are there available for 4? Well, it could have been 4, 3, 2, 1, and 0. So there's 5 choices for that second spot. When you multiply them, there's 30 different ways that you could have made a score, right? So for example, you could have had 4 to 2. You could have had 5 to 0. So there's tons of different options. So that's why we have to look at each spot one at a time. Example number 4. How many different 3-letter arrangements can be made from the letters of the word certain? So we have 3 spots to represent a 3-letter arrangement. If no letter can be used more than once, and each is made up of a vowel between 2 consonants. So we know that this is a vowel, and then the first spot is a consonant, and the last spot is a consonant. So vowels are A, E, I, O, U. Okay, so our vowels here are going to be, we're going to list them as E, A, and I. So that means for the third spot, the vowel, there's 3 choices that could have been there. And for the consonants, we could have had the letter C, R, T, and then N. So there's 4 choices for the first spot. And then when we're rearranging letters, once you use a letter, you can't reuse it. So once I place a consonant in the first spot, I have 1 less consonant for the last spot. So that means there's 3 choices for that last consonant, which if you multiply gives you 36. Now here it says, what if we had to use this word and we're using it with no letters repeated? How many different arrangements can be made? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, so there's 9 spots. So how many letters are there? They're all different, so we know that there's 9 letters for the first spot. We could have an F, an A, a C, E, T, I, O, U, S in that first spot. Any of those letters could have been first. Well, once we use a letter, we have 1 less for the next spot, and so on. And it keeps going down until you get to the last spot, and there's only 1 letter left to be placed. So when we multiply this, we get 362,880. So the next thing we're going to be introduced to is an idea of something called a factorial notation. So what a factorial notation looks like is it looks like an exclamation mark. So n factorial really means that it's a shorter way of writing a number counting down to 1. So for example, n would be the top number, and then you'd multiply it by n minus 1, which is 1 less than the first number, then n minus 2, which is 1 less than the previous number, n minus 3, 1 less than the previous number, all the way down to 1. So that can be rewritten, for example, number 5, where 9 all the way down to 1 multiplied could be the same as saying 9 factorial. So we could use 9 factorial to represent this. So we have buttons in our calculator that can do this for us. Okay, so what you're going to do is you're going to press the number first, your n number, which in our case was 9. Then you're going to press math. You're going to go to the right until it says probability, and then you're going to press the exclamation mark. So wherever you see the exclamation mark is what number you're pressing. So if you press that and press enter, you're going to get 362,880. So that's a way faster way than putting in your calculator 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it saves you time. So this can be used whenever you have the numbers counting down to 1 and your n always is a positive integer. Or you guys know them as, it can be whole numbers. So whole numbers only. So if I have 4 factorial, what that really means is 4 times 3 times 2 times 1. So that would give you the same answer. And then another thing that we need to keep in mind is that 0 factorial, if you put that into your calculator, that's actually equal to 1. So that's a rule that we need to remember. Okay, so let's say you want to figure out 5 friends. How can they line up for a bus? How can they board a bus? Well, again, we would have normally 5 spots with 5, then 4, then 3, then 2, then 1, counting down if we're putting them in a lineup. So, or we can go 5, press math, then we can go to the right until it says probability, and then we can press number 4, enter, and what that does is it gives us the answer of 120. So that's the same as saying 5 factorial. 5, 4, 3, 2, 1, multiply. If all the letters of the word phone are used, how many different 5-letter arrangements can be made beginning with a vowel? Our vowels are O and E. So those are our vowels there. We have 5 spots representing the 5 letters in the word phone. So they're saying we need to start with a vowel. Well, there's 2 choices for our first spot. And it doesn't matter what we have in our next spot, so we have to look at how many letters are left. If we've only used 1 vowel, we have 4 letters left. Then 3, then 2, then 1, because there's no other rules. So this would be the same as simplifying it as 2 multiplied by 4 factorial. 4 factorial just means 4 counting down all the way to 1, and you multiply the numbers together. So if you put that into your calculator, you're going to get 48 as your answer. Example number 8. So we have a volleyball team made up of 6 players stands in line facing a camera for a picture. If Jim and Ed must stand together, how many different arrangements are possible for this picture? So this one's a little tricky because they're saying that Jim and Ed have to stand together. So we're going to put Jim and Ed in the first 2 spots. And then we know that there are 4 other spots for the remaining team members on the volleyball team. So Jim and Ed, if we were to place them in the first 2 spots, well, Jim and Ed could go in the first spot, and whoever is left over could go into the second spot. So this is how you can rearrange Jim and Ed. There's 2 ways to do that. Either Jim goes first or Ed goes first. And then whoever you choose for that first spot, the remaining person, second spot. And then there's 4 people left. So we would write 4, then 3, then 2, then 1. We would get the answer by multiplying. But there's still one more trick. When they're saying that they're standing together, they're not saying that they have to be in the first 2 spots. So what we have to do is say, where could they go? These 2 people could be where they are, so that's 1. They could have gone between these 2 people. They could have gone here between these 2 people. So Jim and Ed could have been here as well between these 2. And then finally, they could have been in the last 2 spots when lining up to take this picture. So in the end, we have to multiply our answer by how many spots Jim and Ed could go in. And there's 5 spots because there's 5 arrows. So to summarize our answer, we're going to say 2 factorial, because that means 2 times 1, times 5 factorial. Because if you look, we have a 5, a 4, 3, 2, 1. So as long as a number counts down all the way to 1, we can use it as a factorial and write it as a factorial. So if you put this into your calculator, you're going to get 240. So In this one, we're just looking at simplifying a factorial notation. So here, what you want to do, the rules are for simplifying is you want to start with the higher one, the bigger one. So n is bigger than n minus 1, so you're going to start with the top. This is bigger, so only start with the bigger one. In this case, bigger, because n is bigger than n minus 3. And then here, bigger. So the bigger one doesn't always have to be at the top. This one is where it's at the top. So that's something to keep in mind. So what we do is we start counting down. After n comes n minus 1. And we're going to stop there and put a factorial. The reason being is we can see the exact same factor in our denominator. And if we see the same factor in our denominator, we can cross them off, leaving us with our answer equal to n, because the factorials will cross each other off as well. So that's the simplified form of n over n minus 1, both of them factorials. So the next one is similar, where we start with n and we count down. But in this case, we have to go further. We have to count down all the way to n minus 3. So we have to keep subtracting 1 until we get to n minus 3, because then it's identical in our denominator. And then we can see that the n minus 3 factorial and the n minus 3 factorial from the top and bottom cross each other off, leaving us with n multiplied by n minus 1 times n minus 2. We could write it like n cubed minus 3n squared plus 2n if we want to, and that's if we did expanding. If we expanded, we would get to this answer. So that's just a way of putting it all together. So that's an option, but you could leave it in factored form if they don't give you specifics. N plus 1 is the bigger one, so we're going to start with n plus 1. After n, meaning if you subtract 1 from n plus 1, you get n. Then if you subtract 1 again, you get n minus 1. And then you'll stop there because it's the same factors at the top and bottom. So the n minus 1 factorials will cross each other off. That will cross itself off with that one, leaving you with n plus 1 multiplied by n, which easily expands to n squared plus n as your final answer. So these ones here, example number 9, they're challenge problems. So they're saying how many odd 4-digit numbers have no repeated digits. So we have 4 spots to represent the 4 digits, and they have no repeated digits. So what is something that we have to keep in mind is that for something to be odd, the last digit is what makes something odd. For example, 23 is odd because the 3 in the last spot is an odd number. Or if I have 1,005, that's an odd number. So first we have to look at how many odd numbers there are. So I could have 1, 3, 5, 7, and 9. So there's 5 choices of odd digits that can go into the last spot. Now we go to the first spot. The first spot is not allowed to be 0, because if I put a 0 there, that would make it a 3-digit number. And the rules say I have to have a 4-digit number. So I can't use 0, and I cannot use the number from last spot, which means that there's 8 choices, because normally I have 10 choices, but because I've taken off 2, meaning 0 is not allowed and the digit that I have in the last spot is not allowed, there's 8 choices left because I cannot repeat, no repeated digits. Now our second digit is allowed to be 0, but we've already used 2 numbers. We've already used something in the last spot and the first spot, which means that from 10 choices, you're subtracting 2, which again gives us 8 choices left. So this is a thinking process. That's why these are more challenging. You have to figure out how many choices are really left. And then our third is a little bit easier, because since we already have 3 numbers taken out of the 10, we now have 7 numbers or 7 digits left. When you multiply all these answers, you should get 2,240 as your answer. And then we have B. It says, how many even 4-digit numbers have no repeated digits? So this is very similar. We have 5 even numbers. And again, you'll still have this 887 from the previous kind of example, because once we've placed a number, we can't use 0 in the first spot, and we can't use that number that we used in the last spot. So that means the answer is actually the same if we talk about even versus odd. And then we have C. How many odd 4-digit numbers can you make using the digits 1 to 7 if the number must be less than 6,000? So for C, C is kind of complicated because we have to do something called cases. We have to look at cases where, what if we use different digits as our odd number, as our last number, which could make it odd. So we're gonna do some cases. So this is case number 1, case number 2, case number 3, and case number 4. So we're saying, what if the last number is a 1? That would be odd, right? So what if the last number is a 1? What if the last number for case number 2 is 3? What if the last number is 5? And finally, what is the case where the last number is 7? So that's going to be important because we need the number to be less than 6,000. So if there's a 1 in the last spot, there's only one choice for all of these, because they're telling us, we're already using the cases to say this is what the number is. So in the first case, there's only one choice because it has to be a 1. Second case, it has to be a 3. So that's one number that's possible there. Now, if you place a 1 in your last spot, there's 5 choices left for your first number, because that means you can have 2, 3, 4, 5, 6, actually there's 4 choices left, because it says you can use the digits 1 to 7 if the number must be less than 6,000. No digits are repeated. So if the last number is a 1, we're allowed to use the numbers 2, 3, 4, 5. So we can't use 1. We can use 2, 3, 4, and 5. Yeah, because we can't use a 6, because if we put a 6 in that spot, meaning the number 6 in that spot, that's going to give us a number that's more than 6,000. So we're only allowed to have the numbers being, it'll be something like 2,000, 3,000, 4,000, 5,000. So that's 4 different options for your first spot. And then we'll go to case number 2, where if we have a 3 in that last spot, now we're allowed to have 1, meaning 1,000, 2,000. We can't have 3,000, so we'll skip over that. We can have the number 5,000. So we can have 1,000, 2,000, not 3, 4, 5. Yeah, so there's 4 choices for the first spot again. And then if we have a 5 in the last spot, we're allowed to have 1,000, 2,000, 3,000, 4,000. So there's 4 choices for the first spot. And then if the last number is a 7, this is where it's interesting, because we actually have 5 options, because we're allowed to put a 1, 2, 3, 4, 5 in that spot, and all of those numbers, that would make it less than 6,000 still. So there's actually 5 choices for the first spot, so it doesn't run like the other ones. Now let's go to the next digit. Now, since we have 1 through 7 that can be allowed, we've already used 2 numbers for each of these cases. So that means the second digit, there's 5 choices for all of these second spots. So Normally there's 7 numbers, but since I already filled in 2 spots, there's 2 less from 7. So that means 5 numbers left. And then for our third spot, there's 4, 4, 4, 4, because 1 less than that previous number. Now what we want to do is we're going to have to multiply all of these. We know that this one's going to equal 80, 80, 80, and this one is going to be 100. So what we have to do with all these answers is add them up, and we're going to get 340 total ways that we can make this 4-digit number. So those are the different answers. So as you can see, this is a really challenging one because you have to look at what can go in the last spot, what can go in the first spot, and so those are some good thinking ones. Question D, it says 5 people are seated on a bench, and how many ways can they be seated if E is in the middle? Well, if E is in the middle, we have one choice for that middle spot. And then the remaining people, it really doesn't matter. So it's 4, 3, 2, 1 around that middle person. So what we'll notice is that we just have the answer of 4 factorial because there's 4, 3, 2, 1 multiplied, which is 4 factorial. And then multiplying that answer by 1 doesn't change the answer. So that's going to equal 24 if we multiply. So that's for 1. Part 2 is where A and B must be seated together. So just like in the example that we had for example 8, I like to put them together. So that means A and B are seated together, so we would put 2, 1 because there's 2 ways and then 1 way that we can arrange the letters A, B, or people A, B. And there's 3 spots left, so 3, 2, 1. 3 people, then 2, then 1. And finally, we always multiply by how many spots these guys can go into. So these 2 people can go first, second, third, or fourth in this arrangement. So there's 4 places that they can go into. And so to summarize this, we would say 2 factorial multiplied by 4 factorial. So the 2 factorial is right there, 2, 1. And then the 4 factorial is 4, 3, 2, 1. So then when we multiply those answers together, we should get 48. And our third part is what if they can't be seated together? So this is where we don't really use any kind of, we can't really arrange that. It's too hard to figure that out. So what I like to do is I like to find out the total and subtract where they are seated together. And what that will do is it'll give us the complement, meaning when they're not seated together. So the total ways we could ever arrange these people would be 5 factorial. And then what we're doing is subtracting our answer from the previous one, which was 48 arrangements. So 120 minus 48 ways that they are seated together will give us 72 ways where they are not together. So that's kind of the best and easiest way to figure those ones out. Now, permutation, we can use one more way to represent a permutation, where permutation means order does matter. Order matters whenever we look at rearranging letters of a word, when we look at passwords, when we look at combination locks. There's different things that we have to keep in mind. So those order does matter when we do things like that. So we have to use this NPR. So NPR is similar to that factorial notation. So if I did 4 factorial, that would be like saying there's 4 choices going into 4 spots. So in our calculators, a way of putting that in just to show you that they are equivalent, if I put 4 math probability, number 4, I get 24. And then if I put 4 math probability, number 2, which is NPR, and then put 4 spots, that also gives me the exact same answer. So this is just another way of calculating where how many ways we have to put something into a certain number of spots. So example number 10, we have the letters of the word product. How many 4-letter arrangements can be made? So this is where I can write it as 7p4. The reason being is there's 7 letters in the word product, and I have to make a 4-letter arrangement. So this is how many choices I have, and 4 represents how many spots I'm putting them into. So if I put that into my calculator by going 7p4, so I'll show you what I'm doing. I'm putting 7 first, math, probability, go to number 2, and then press 4. The answer is 840. Determine the number of arrangements of 4 or more letters that can be formed. So this is where we have cases. So case 1 is where we have 4 letters. Case 2, we can have 5 letters. Case 3, we can have 6 letters. Case 4, we can have 7 letters, because we're trying to use the letters of the word logarithm. And there's actually 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So that means we have a few more cases. We're going to have to do case 5 is where we use 8 letters. Case 6 is where we use 9 letters. So those are all the cases that we have. So 4 letters, using 4 letters from the word logarithm is where we would say 9 letters to choose from, put into 4 spots. So we would put 9p4, and we would get the answer. And then our next one would be 9p5, 9 letters in logarithm used for 6 spots, 9p7, 9p8, and 9p9. So you would put this all into your calculator by adding them, and it would give you, when you added them, you'd get 985,824. Example number 11 says, how many 6-letter words can be formed from the letters of travel? The letters cannot be repeated. So for A, we would just have to write 6 factorial, or it will be equal to 6p6. So that would be equal to 720 if we put it in our calculator. B, they're saying, what if the first letter must be an L? Well, that means that the first spot will have 1 choice only, and then we're going to have 5 other letters to rearrange, so that's going to be 5 factorial. So that's equal to 120. So when they tell you something has to go in a certain spot, there's only one way that that can happen. That's why I put a 1 for that L. C, we have if the second and fourth letter are vowels. So 1, 2, 3, 4, 5, 6. I sometimes like to write these spaces out to help me to see how visually that looks like. So vowels will be the letters A, E. So the second and the fourth letter are vowels. It's just like how it is right now. So either A or E could go into the second spot, and then for the fourth spot we have only 1 choice left, meaning if we had A or E here, and let's say we picked A to go there, then E would have to go there, which means there's only 1 choice for that fourth spot vowel. And then we still have 4 more letters left, so that would be 4 times 3 times 2 times 1 if we were to rearrange those. So what we would do is we would look at, well, there's factorials. 4, 3, 2, 1 represents the factorial of 4 factorial, multiplied by the other factorial I see would be 2 times 1. So that's 2 factorial. If I put that in my calculator, that is 48. And then D, if an A and a V must be adjacent beside each other. So adjacent just means side by side. So this is where I have 6 letters, 6 spots. I'll first start by placing the A and V in the first 2 spots, so that's represented by 2 times 1. So that's equal to 2 factorial. And then the remaining letters will be 4, 3, 2, 1, rearranged, 4 factorial. Now we always need to multiply by how many spots they can go into. And so the spots will be represented by 1, 2, 3, 4, 5, always around the 4, 3, 2, 1. The remaining pieces that are left, it will go around it. So there's actually 5 spots to place A and V into. So to summarize this, we would say 2 factorial times 5 factorial, because these two guys are equal to 5 factorial, 5, 4, 3, 2, 1. If you put that into your calculator, that's equal to 240 different arrangements. So example number 12, they're asking us to solve for n. So what we're going to do is on your formula sheet, we have a formula that looks like this. NPR is the same as saying n factorial over n minus r factorial. So we're going to use that and replace the letters into the right spots, or the numbers in the right spots. So for A, we have NP2. So n is going to stay as it is, but r is going to be replaced with 2, and that's going to equal 56. So just like in the previous kind of examples, in example number where it says calculate with factorial notations over here, in this part we simplified. We're going to do the same thing for this example right here. We're going to simplify n by counting down. So after n comes n minus 1. After n minus 1 comes n minus 2. Factorial, we stop there because it gives us the exact same thing at the bottom. The goal here is to get rid of the factorials by crossing them off. And we know that the right side is 56. So now we have n multiplied by n minus 1, which is n squared minus n, equals 56. Bring the 56 to the left side, and now we have a quadratic equation that we can solve for. When we factor this, this will give us n minus 8 and n plus 7 equals 0. So that means n could equal 8, or it could equal negative 7. Negatives are not allowed to be factorials in this case. So if I were to put that into my calculator, it would give me an error. So negative 7 should be crossed off. It does not work. B, same idea, but now we just have 30. So we're using the exact same steps on the left, but instead of 56, put a 30. Those cross off, leaving us with n squared minus n, and then we're going to bring the 30 over to become minus 30, which is equal to 0. That can factor as n minus 6 and n plus 5 equaling 0. N equals 6 is one solution, and n equals negative 5 is another possibility, where the n is not allowed to be negative, so I would cross that answer off. Question C. We have now two sides of it. So we're going to have n factorial over n minus r, which is 4 factorial on the left, 8 multiplied by n minus 1 factorial. So that whatever comes here needs to replace your n. So that's why I put n minus 1 in brackets at the top, divided by n minus r, which is n minus 1, minus r, which is 3 factorial at the bottom. So we're just going to simplify the left side. Remember that counts down all the way until we get to the bottom. So I keep counting down until the n minus 4s cross each other off. So now I have n minus 1, n minus 2, and n minus 3 left over on the left. On the right, I'm going to write n, 8 times n minus 1 factorial over n minus 1 minus 3 is minus 4 factorial. So just like on the left side, I'm going to count down the n minus 1 until I get to n minus 4. So first it's n minus 1, then it's n minus 2, n minus 3, and then the 4, n minus 4 would cross each other off, so I don't need to write that. Another thing you should notice is that if you have the exact same factors on the left and right side, they will cross each other off. So those will cross each other off, the n minus 2's will cross each other off, and the n minus 1's will cross each other off, leaving us with a final answer of just n by itself on the left equaling 8. So this is our final answer. Example number 13, it says, how many 4-letter arrangements can be made using the letters of peer? So this one's different. Why? Because we have something called repetition. We have repeating identical letters. So what we do is we start the question previously, as previous, where we count how many letters are and we would say factorial. This means 4, then 3, then 2, then 1 ways of rearranging peer. But we need to divide by how many letters there are repeating. There are 2 e's repeating, so I have to write 2 factorial, and that's divided out. So if I put this into my calculator, I'm going to get 12. So we always, hint, need to divide out identical or repeating items. It doesn't have to be letters, it can be things as well. If they say identical, we need to keep that in mind. So that's what they're telling us to do for the next examples right here, is divide out repetition. So if A and B are one kind of thing that's alike, and another thing that's alike is B, and another thing alike that is C, we have to divide that out. So let's look at the word poppies. As you can see right away, we have these 3 P's. They're going to have to be divided out in every single part. No matter what the rules are, you have to divide out that repetition. So if there's no rules, you would count how many letters there are, factorial, and divide it by how many letters are repeating, which are 3 of the same. So there's 3 repeating P's, and you would put that in your calculator, and that would give you 840 arrangements. Now, if you start with a P, you might want to do spots for this to kind of see where this is going. The first spot, there's going to be 3 choices because there are 3 P's. And now, since you used one of the P's, you would say 6, 5, 4, 3, 2, 1. You treat it just like a regular question, because in the end, you're going to write 3 times 6 factorial is going to be divided by the 3 repeating letters, 3 factorial, and that will give you your final answer. So we kind of treat it like a regular question, and then just have to include that division by repetition. Now, if the first 2 letters are a P, that means we're going to have first 2 letters are P, that means we have 3, then 2 choices. And then how many letters are left? There's 5, 4, 3, 2, 1 letters left. So that's going to be 3 times 2 is 6, multiplied by 5, 4, 3, 2, 1 is 5 factorial. Then you would always, again, just like the previous questions, divide by the 3 repeating P's. And that would give you an answer of 120. Now, what if all 3 P's are together? Well, this is like when 2 people are together. They have to be in the first 3 spots. So I'm going to put the first 3 spots as P's, 3, 2, 1. And then the remaining spots, there's still 4 spots left. That will be the remaining letters. So that would be like the O, the I, E, S. So 4, 3, 2, 1. Now we always multiply it by how many spots the P's can go into. They can be first, in between the first and second, in between the second and third, in between the third and fourth, and then last. So there's actually 5 numbers that we want to, or 5 spots that they can go into. So to summarize, it's going to be 3 factorial multiplied by 5 factorial, because I see that there is a 5, 4, 3, 2, 1 multiplied, which is a factorial notation. So if you put that into your calculator, you need to also divide by the repetition. If you don't do that, you will get the wrong answer. So that's going to give you 120 if you put that in. If the first letter is a P and the second letter is not a P. So we have 3 choices for the first spot. And for the second spot, we can't put a P there. So instead of there being a 5 in this second spot, we're going to put a 4. Because now that all the P's are gone, if you take out all the P's, there's only 4 letters that are allowed in that second spot. And now, since you've already used a P and 1 other letter, now you have 5 choices left for the first spot. So 5, and then it continues like regular where you count down by subtracting 1 to get the other numbers. You're going to multiply these numbers together to get the top as 1440, and you're still going to divide it by that 3 factorial because that's the repetition of the 3 P's. You're going to get an answer of 240 if you're doing it properly. Example number 15, we have 2 mathematics posters must be together at the end. So we know that they're going to be at the end, so that does help us to draw this out, but we do see that there's identical things. We have 2 identical math posters and 3 identical science posters. So for A, we're going to have 6 spots. 1, 2, 3, 4, 5, 6. It says the 2 math posters must be together at the end, so we're going to write 2, 1 at the very end. Now there's still 4 posters left, so we can go 4, 3, 2, 1 for the remaining spots. Now with this answer, that's going to be the same as saying 4 factorial times 2 factorial. We're going to have to divide by the repetition. Now there's 2 types of repetition. They have to be kept separately. There's 2 mathematics posters that are the same, and then there's 3 science posters that are the same. We actually have to write them one at a time as factorials, because if we wrote them as 5 factorial, that would just mean that there's 5 identical posters, but there's not. There's 2 different types of identical posters. So when we put this in our calculator, in the end, so we're also going to have to do one more thing. We're going to have to flip it around and multiply this answer by 2 because there's 2 ends. It says that it has to be on an end. It doesn't tell us which end. So it could have been on this end, or we could have started and recreated this whole question with them on the other end. So that means we have to multiply our answer by 2 because there are 2 ends to this, and that's going to give us an answer of 8. B, it says the 3 science posters must be together. So if they're together, you're going to have 3 factorial for them being in the first 3 spots, 3 factorial for the other posters being rearranged, and then there's going to be 4 spots that the identical science posters can go into. So what that looks like, if you want to see the spots, is these are the 3 science, and then these are the 3 other. And then the science can go first, second, third, or fourth. So that's what the 4 represents. And then you're always dividing it by that 2 factorial, 3 factorial for this entire question for A, B, and C. So you should be getting an answer of 12. And C, the 3 science posters can't be together. So we're going to use the answer for B and subtract it from our total. So if you go total minus our previous answer, which was 12, where the science posters were together, we're going to get the answer. So the total comes from making up no rules. Well, we know that there's 6 posters rearranged, so we would say 6 factorial, and then we would divide it by the 3 factorial, 2 factorial of the repetition. That doesn't go away no matter what you do. So if you take that, that's going to be equal to 60 minus 12, which is 48. So that means that there is 48 ways that the science posters can't be together. Example number 16, they're saying how many different 5-digit numbers can be made by arranging all the digits of these numbers. So as you can see, there's 5 digits. So you would say 5 factorial if you were to rearrange them. But as you can see, there are identical numbers. There are 2 7s, so we have to divide those out. And there's 3 1s that have to be divided out. So how many of them there are has to be divided with a factorial notation. So that's going to be 120 to represent 5 factorial and 12 to represent 2 factorial times 3 factorial. So that's going to be 10 as an answer. So there's 10 different 5-digit numbers that can be created by rearranging those. Pathways. So pathways are saying how do we go from one letter to another letter? So from A to B, how do we get there? So we're going to use something called Pascal's triangle. So what I like to do is I like to start with, it says to follow from A to B. So there's one way to go along the sides of a rectangle. So you're saying there's only one route that I would take to go here, 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 here. It's only one road. Same thing here. There's one road here, one road that you're taking to get to all these points. There's no other roads that take you there. Now, the next part is, well, if you look over here, there's actually 2 rows to get to this point. Where they meet, there's 2 roads that take you there because you always have to be going towards B. So we would say 2. And that came from taking 1 plus 1 and adding it together to get 2. Now our next one, we would look and say, well, I can take this road to get here. I can take this road to get here. And then finally, I can actually take this road to get there. So there's actually 3 routes to get to that point. So 3 routes to get here. And if you notice, the 2 numbers that come towards it, the 1 and the 2 add up to give me 3. So if you keep that in mind, it will help you. So for example, 2 and 1 add up to 3 as well. So this should be a 3. And then we have 3 plus 1 adds up to 4. 4 plus 1 adds up to 5. 3 plus 3, do you see the 3's coming towards that intersection will add up to 6. 6 plus 4 adds up to 10. 10 plus 5 adds up to 15. And you're just always adding the numbers coming toward it. And that should give you the intersection pieces. So we're only looking at the intersections. So 1 plus 4 is 5. 5 plus 10 is 15. 20 plus 15 is 35. 35 plus 35 is 70. 1 plus 5 is 6. 15 plus 6 is 21. 21 plus 35 is 56. 56 plus 70 is 126. 1 plus 6 is 7. 7 plus 21 is 28. 28 plus 56 is 84. And those 2 numbers finally add up to the intersection being 210. And that's your final answer. So how many paths can you follow for the return trip? So from A to B and B to A, so it would be the same. If you went from B to A in this case, it would be the exact same answer if you switched it for that one. Sometimes it could be different, so it's not always the same. So you do want to follow which way it's going. So if it says A to B, go from A to B. Always go towards that second letter. Now for these ones, there's a faster way to do these kinds of questions if it's a nice box. So I'll show you first the fast method, and then I'll show you how to do it with the above Pascal's method. Okay, so this one's wanting us to go from A to B, so only going towards B in that direction. So what you would do is you count up the total boxes to get from A to B within each box. So for box number 1, you'd have to go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 blocks to take you from that to the intersection between the second box. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 factorial. Dividing by the side length. So the side lengths will be this side length, 1, 2, 3, 4. So there's 4 blocks. That's like the repetition. Divided by 1, 2, 3, 4, 5. 5 factorial. So this was a 4 factorial by 5 factorial box there. And the addition of those two numbers is what you put at the top. Now you're going to multiply it with the next box because it's going to continue on. So as you can see, I can go from here to here with a total of 4 blocks. So 4 factorial divided by its side lengths of its box are going to be 2 by 2. It's a 2 by 2 box. The total to get from that point right here to the B, if you count out the sides, that's going to be 6 factorial divided by the box dimensions will be a 3 factorial by a 3 factorial. Now if you put this all into your calculator, you'll get that this is equal to 15,120. So 15,120. So what I'll do is I'll show you that you can get this exact same answer using Pascal's triangle. It just might take a little bit longer, and that's the only trick to it. Okay, so we're still going in the direction of A to B. So along the side lengths, I have 1s, because there's only one way to get there. Once I do the direct side lengths, then I start adding up. 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6. So I'm adding up the numbers coming towards that intersection point to get what the intersection adds up to. 10 plus 5 is 15, 15 plus 6 is 21, 1 plus 3 is 4, this one's 10, 20, 35, then we have, that's going to be 56, 1 plus 4 is 5, 5 plus 1 is 15, and we have 35, 70, and 70 plus 56 adds up to 126. Now what you'll notice is that this is now the only number coming towards these sides here. So since those are the only numbers coming toward it, the side lengths of your second box are going to be 126, directly going forward. So it's not going to be the side lengths of all the parts, it's just those direct kind of lines with it. And then 126 plus 126 is 252. 252 plus 126 is 378. And then we just keep adding. 378 plus 378 is 756. And now, just like before, those are the only side lengths going forward, so you put 756. Because what's happening is there's no number coming down towards that 756, so it's like adding a 0 to that number, so it doesn't change. Directly below all these will be 756 as well. There's only 756 ways to get down this road. And then we keep going. So 756 plus 756 is 1512. $756 plus 1512, 2268. 2268 plus 756, 3024. Then we have 2268 again, 4536, 7560 when you add them, 3024, 7500, and finally 1500 and 120. So that's 15,120, and that matches the answer. So as you can see, this took way longer than using this method right here. But you can't use this method here unless they're nice, perfect boxes that aren't overlapping. So they have to be like connected this way, and that's the only way to actually do it. Example number 19, they're saying, how do I go from A to B? Well, to get to this point right here, we have to see how many roots there are. There are 1, 2, 3, 4 possible ways to get to this point right there. And then there are 2 possible routes to get to point B. And we're going to multiply between the answers because you have to say and. We have to go through these points together to get our final answer, and that's going to be 8 different routes. So there's 8 routes in total. So for this B question, you can actually use Pascal's triangle again, because we're going and saying, well, there's one way to get to these points. So in between the triangles, those are routes that we're taking. Here, that would be a 1, and here, that would be a 1 along the sides. So along the sides, there's only one way to get to those points. Now, if you look, these two numbers add together to give you 2. And then 1 plus 2 adds to 3. 2 plus 1 adds to 3. And then 1 plus 3 adds to 4. 3 plus 3 adds to 6. 3 plus 1 adds to 4. And then 4 plus 6 adds to 10. 6 plus 4 adds to 10. 4 plus 1 adds to 5. 10 plus 10 adds to 20. 10 plus 5 adds to 15. And then finally 5 plus 1 adds to 6. We're going to add these numbers up. So 20, which is at A, B, which is at 15, and C, which is 6. If you add them up, there's 41 possible pathways for the ball to reach the exit. And so as you can see, these are just some pathway practice questions that you can try, and the answers are below if you want to check them out. So that's it for lesson 11.1. There's only 2 more